Okay, we're going to be looking at 4.3, which is the fundamental theorem of calculus. And I hope that sounds important. The fundamental theorem of calculus. It's like the fundamental theorem of the whole entire class, right? And so that's going to be our story in this section. So this is the paper review of 4.3. And maybe on this one, I need to back out a time. Maybe I'll back out after we find some of these values. So they're saying to let g at x equal the integral from 0 to x of f at t dt, where x is the function whose graph is shown below. And they're asking us to evaluate g at x for these values right here. This is problem 2 in your textbook on 4.3. And so I don't want to have to write all of these up here, and I should have given more room, but I'm going to write it down here, down below here, just so that you can see. So g at x equals the interval from 0 to x of f at t dt, so that if they ask me to find g at 0, then you're going to go and everywhere you see x, you're going to replace 0. So this is going to be me finding the integral from 0 to 0 of f of t dt. Now, one of the properties I had that it was no matter what the function is, if your bounds are 0 to 0, if your bounds are the same, that this was equal to 0. So I'm going to put that right up here in my chart. That's 0. And so then g at 1, so that's going to be the integral from 0 to 1 of f of, I put x there, but that was a t, sorry. And then I didn't catch it because it didn't matter. So g at 1, 0 to 1 of f at t dt. And then now what I'm going to have to use in order to find this integral here, because the bounds aren't the same, is I'm going to have to use the picture they gave me. And remember, the integral is the area under the curve. And so we're finding this area from on the x-axis from 0 to 1, right? Because that's where our bounds went from, 0 to 1. And this is the area I'm trying to find. So sorry, if Kevin can cut that out, that space, he will. I wasn't allowing you to just find that. I hope that you did find that area, but someone was texting me something that I needed to tell them because they're in a little tiny bit of an emergency, but not a big emergency. If it was a real emergency, I would stop the video, but they just needed a number that I needed to give them so that they can solve their emergency. So I did that. Okay, sorry about that. So this area is half. And then g at 2, so I'm going to go down here and find g at 2. So g at 2 is the integral. Remember, everywhere you see x, you're going to put 2, so this is going to be 0 to 2 of f of t dt. And I'm going to have to go find this area using my chart over here. So from 0 to 2, so here's to 2. And I hope that you're noticing, just like I'm noticing, that if I shade the area trapped between the x-axis and the curve, that I have the same amount above the x-axis as I have below the x-axis. So this would be counted as positive, and this would be counted as negative. And when you put them together, you get 0, since it's exactly the same amount. And then now I'm going to go to 3. And so sometimes this function that they have going right here that they're showing you is called the area so far function. And you can kind of see that I'm just building on, because as I go to 3, right? So here's to 3. This area together, net area together, made 0. And if you put this area here, it's below the axis, so it's going to be counted as negative. And that area is half, so negative half. And then I'm going to go over to 4, right? It's from 0 to 4. And when I go over to 4, this is the area that we're now looking at. And now we have 2 half areas that are above and 2 that are below. So that makes 0 again. And then to 5. So we had 0. So all I have to do is find from 4 to 5. And that will be the same as the area from 0 to 5. Since the other pieces, you can kind of go them along. So as we go along here, you can see that that's perfectly half, and then this is an area of 1, so this is 1.5. So this made 0, this made 0, and then now I have 1.5, which I can write as 1.5, or I can write as 1.5. Either way is good, so I'm going to write 1.5. Now I'm going to go to 6. And 6 keeps adding on. And so we already had that this area right here was 1.5, right? And now we're going to add on, and it looks like to me, and it's nice, they made it nice so that we could find the area quickly. We're going to add on another 2.5. So we have from 0 to 6, we have 0 and 0 and 1.5 and 2.5, which should make 4. And then in a move I wouldn't have thought that the book would have done, but they did do. They've given us to 7, which is here, and this area here is I need to add on, but you can see that because it's a little bit curved, that I wouldn't be able to find it exactly. And so will I be able to find it exactly? Well, if I can write the equation of that, I can. It looks to me like it's a parabola is what it's looking like. It is, but that's not what they're hoping. They're hoping I'll just kind of estimate it. So to the best of my ability, this is almost a whole box, right? And then this area right here is more than half a box. And then this area right here is a little bit less than half a box. And you can be as accurate as you want to be. To me, that when I put this area together here that's in this box with this area right here that's in this box, it is more than one whole box, because that little spot right there and that little spot over this spot's a little tiny bit bigger than that, but not a ton bigger. And then when I count off that this was lopped off of it as well, I don't know, I'm around 2. I mean, that's what I'm kind of estimating that to be, 2. I don't know what it is. If you thought it was something different than 2, oh, wait a minute. You're like, wait a minute, what are you doing? From 6 to 7 is 2, but remember that G of 7, I'm writing them down here, right? G of 7 equals 0 to 7 of f of t dt, which is equal to all of it added up, right? And so I started saying that was 2 because I was estimating away and I got crazy. But here, this is equal to 0. This is equal to 0. I need to add all of them together. And this is 1.5 plus 2.5, which I said was 4, plus 2 more is 6. So this altogether is 6. So the distance from 0 to 7 is 6, is what are the area that's trapped, the net area. That's what the integral finds, is the net area is around 6. So they ask us, where does G have a minimum value? And so they want to know And we can kind of look at this just to kind of see, and then see if we think that there's something that we haven't caught that's even more minimum than that. So it looks to me like G at 3 is the minimum value. So I'm going to be asking you, does it get any, is there any place? Now, remember, G goes from 0 to X. Is there any place that is going to be more negative than 1/2? So here, the reason that it's negative is because there's more area below the curve than there is above the below the x-axis than there is above the x-axis. So remember, we're finding the area trapped by the curve and the x-axis. I know the curve's not very curvy here; it's a straight line, except for over here, it does curve. And so, because all of this is positive over here, it's you know what I mean. This is positive here. All of these would be this would be because it's smaller, and than the area that's already up here. And remember, we have to go from 0 to a value. I think G at 3 is actually the minimum value, not the maximum value. Sorry, I was finding the minimum value. So G at 3 is the only place that it's negative and the most negative it is. So that's our minimum value. So this is G at 3 equals negative 1/2. Okay, the maximum value, that's where we want the most area above the x-axis. And you can kind of see that, and remember, we have to go 0 to, so definitely 0 to 7, because that just gets this area just gets bigger and bigger. So G at 7, which was, we estimated to be 6. And then they wanted us to sketch G, which is the so far function. So I'm going to be sketching these points. So 0, 0, I'm going to sketch. So 0, 0 right here. And 1, 1/2. So over 1 up half right here. Over 2 up 0 right there. Over 3 down 1/2 here. Over 4 up 0 here. Over 5 up 1.5. There's 1.5. And over 6 up 4. And over 7, so here's 7, up 6. And so they were just hoping that I would do a little sketch of that. And so I have these points. I haven't found any values in between. And so if you wanted to go and find some values in between, you could. Not that I want to do that, but like you could go and find G at 1/2, which would be, G at 1/2 would be the integral from 0 to 1/2 of, and then f of t dt, right? And then if I go here and go here to half, then I'm finding that area right there. And it's a little trapezoid. And so I probably could find that area. And I don't know that I care to, though, but I definitely could find that area. So, anyway, sorry, we have a little tiny emergency that doesn't really involve me other than needing numbers and advice from me. Nothing I can do about it. Makes me want to start this video again, but they're gonna let me know. What I was trying to say is how do these connect with one another? I do know that it's continuous. The area is continuous. And how do they connect with one another? Is it a straight line, or is it a smooth curved line? or whatever have you. And and just kind of looking at it as I kind of go along, I don't think that I'm going to be have the stamina to come up with more points, right? But would you agree with me that if I just go halfway, that is more than half of the area um, that I had here? And so this is not really a straight line, because if it was exactly straight, then that would, if it was exactly halfway, then it would make me feel it's a straight line. But I don't know exactly how it kind of curves. And you know what? They weren't really into that. They weren't caring that much about it. So I'm just kind of connecting them here. And so if you wanted to get a better idea of, does this go straight there? It doesn't. It probably curves a little. And I was just trying to show you that it probably wasn't straight, because if I go halfway, that's more than half of the area. But it doesn't matter that much. That's that you know that that's this is they what they wanted out of us is they wanted to reinforce that the area trapped between the x-axis and the curve is the integral. So we definitely reinforce that, and that the integral can be a function. And here's this function right here. It passes the vertical line test, you know what I mean? And I've graphed it, and it's a function. So that's what they wanted you to know. And so exactly how it looks and whether or not it's made of straight line segments or not straight line segments is not, that wasn't their main concern. But actually it is a smooth curve. I think it is a smooth curve because this area right here, it's not going to be straight because it's not half. Anyway, okay, not making a big deal out of that though, but you're like, yeah, you did. You made a big deal out of it. Okay. And then it was discovered that integration and differentiation are inverse processes. So, and so finding the problem of the tangent lines and the problem of the area are inverses of one another, and that's not something that people saw coming. And so there were people, and they were looking at the tangent applications of calculus, and uh, um, so so goodness gracious, making me hard to think. Okay, so there were people that were looking at the differential calculus, and they were looking at the tangent line problems and all of the things that you could find with the tangent line problems, and that all concerned instantaneous rates of change and slopes of curves. That's what that all went with. And then there were other people that were concerned. They were studying math, and we're talking 200 or 300 years ago, and they were investigating integral calculus, and that concerned the accumulation of quantities and the areas under the curve and between curves. So that's what they were looking at, and how you could find a Riemann sum to find the area between the x-axis and a curve, or between two curves, and could you do it with other things, and all of that. So you had two different groups of people studying this, one group studying this and one group studying this, and then this guy came along and he said, hey, you guys realize that these two things are inverses of one another. And like add and subtract are inverses of one another, and multiply and divide are inverses of one another, and squaring and square rooting are inverses of one another. And it blew people's minds because they did not see that coming. So they did not see that the integral was the antiderivative. So they didn't see that coming. So differentiation, I cannot say that when I'm on video. I probably don't say it very well in class either, and the integration are inverse processes. And so this is the fundamental theorem of calculus part 1, and that's basically what the fundamental theorem of calculus part 1 is saying. And so So it says if f is a continuous function on an interval a to b, then this function defined like this, so this function g is an integral. So we have some function f and g, here it is, the function f right there, and g is the integral of that function. And then they say that this will be, g at x would be continuous on the integral a to b and is differentiable. So when you take the derivative of, when you take the derivative of g, you get f is what you get. And so that the derivative of this integral, because that's what g is, this integral is equal to f at x. And so just to be clear of what they're saying is that they had this right here, and then when they take the derivative of g, so that's taking the derivative of this integral with respect to x, and this integral had t in it, t is a dummy variable, you get g prime at x equals f of x, because they're inverse processes of one another. And so it undoes, this d dx undoes that integral and just gives you the function evaluated at x. And so whatever your upper bound there was x. This can be, down here they're saying 0, but that can be any constant. If you want to see a proof of the fundamental theorem of calculus, then you can go here and you can look at a proof of the fundamental theorem of calculus, if you like. There's probably also a proof of the fundamental theorem of calculus in your textbook. And so balancing between all of the theory, I guess, proving it and doing examples, is me here in the center. So if you come to my office and you want to look at the proof together, I'm willing. But why I'm doing examples is because that's what I ask you on the test. And so that you would have practice at doing your examples. Okay, so what this said here, I'm going to write the fundamental theorem of calculus right up here. It said that if g at x equaled the integral from some constant, I'm going to write a constant down here, that could be 1 or 0 or whatever have you, to x, x, I'm at the top of the page, and then I have some function f at t, dt, then this is the fundamental theorem of calculus part 1, then the derivative of g is equal to, all I have to do is plug in x into f at x. And the taking the derivative of the integral undoes it. So it's just like if I asked you to add 7 to your age, and then I said, even 10 minutes later, now take away 7 from your age, then I've asked you to apply inverses. And so you're just going to get back your age. So here, that's what they're asking you to do. They're giving you an integral, and they're saying, find the derivative of it. And so, and this is the notation that they've chose to use, and they've asked you to find the derivative in words. Another way that they could ask you to find the derivative is they could have asked you to find g prime at x, and then not use words to find it. They could have just said, find g prime at x for number 10. For 14, it would be something different because of different variables kind of going around. And so be careful, because when you go look at the problems, they're going to do both. They're going to ask you in words, and they're going to ask you like this as well. So when I go to find the derivative, I'm like, okay, I have to make sure that I can use the fundamental theorem of calculus. So this has to be a constant, and that has to be a variable of x, and then and this is some function at another variable, t or u or p or y, whatever the other variable is. And so I guess this one's at t. Then and then all you do to find the derivative is they undo one another. And this would be equal to, I just replace t with x. So cosine into the function. So into the function, all I do is replace t with x. and this would be x squared. And then that's it. And you're like, okay, that's too weird. That's too easy. All it's saying is they're inverses of one another, but it's just like the birthday problem. If I asked you to add a really horrible thing to your age, and then I asked you to subtract the really horrible thing from your age, you just get your age, right? Because they're inverses of one another. Here they've changed the variables around just to make sure that we understand what we got going. And so they would be asking us to find r prime is what they would be asking us to find. And uh, and so we're gonna do that. Now, what you have to use the fundamental theorem of calculus is you have to have a constant down here at the bottom, and you have to have your variable up here at the top. And you notice, oh, they tried to trick me here. They switched that. But don't worry, you have a way of switching it back. That was a property that you had, and that property said that if you switch the bounds, then you just have to put a what out in front. So that's what I want to do, is I want to switch the bounds so I can use the fundamental theorem of calculus. So I put a negative out in front. So this is going to go from 2 to y of t to the third sine of t dt. And when I go to find the derivative, so that'd be r prime at y. I could also write that dr dy. So that would be another way that I could write this if I wanted. Dr dy would be another way of writing it. The negative just holds still, right? So the negative's just holding still. I'm going to put my finger on it. And now this is where I'm going to apply the fundamental theorem of calculus. It said that if you're trying to take the derivative of something like this, it's an integral, then you have to make sure that this down here is a constant, and it is. And they had said 0, but it's not just 0. It could be any constant. And so I have a constant down there. And then whatever you have up here, all you do with what you have up here is you plug it in for t. You replace it in, it's the input into t. So this would be y to the third sine of y. And that's it. And of course, if you wanted to use the notation dr dy, and so also know that they could ask you to find dr dy, right? And that would have been this, minus y to the third sine of t, sine of y. So, so that's the fundamental theorem of calculus. It's for sure going to be on your test because inverses undo one another, and it's the fundamental theorem of calculus. Is the most important theorem in calculus, one of the most important theorems in calculus. And so for certain it will be on your test. But what I want to make sure of that everyone sees is that it just takes some getting used to. It's not particularly hard. Now I want to talk about something else just for a second. I want to talk about finding the derivative because they're going to make it more complicated, as you can probably see by the next examples, problem 18. So I have this example to mock problem 18, and then we'll do problem 18 from your book. And you notice the difference. You know, I'm going from 0 to x, and I'm going from 0 to x to the fourth. And remember that this x becomes the inside function. And so that means this x becomes the inside function. And so the reason that I wanted to write this out is because I wanted to remind you about the chain rule. And your book really doesn't talk about the chain rule. They just start asking you questions about it. And so I kind of was a little disappointed in the way they handled that because that's the hard part of it. And they just asked you questions on it. They didn't really talk about it. So I just wanted to remind you, if I was going to take the derivative of the function, I had y equals sine of x, then I can write either y prime or dy dx, what your choice. So I'm going to write y prime equals, and then this is cosine of x. But when I go to find the derivative of this, because I have x to the fourth, I have to use the chain rule. And so how this looks when I have to use the chain rule, so I'm going to write a note to myself that I have to use the chain rule. And the chain rule has an outside function. And that outside function is sine, right, of what I'm going to plug in there, which is x to the fourth, what I'm going to substitute in, right? And the inside function is what I'm going to substitute in, which is x to the fourth. And what you have to do to find the derivative, so the derivative of y is y prime, whatever notation makes you happy. the derivative of the outside function is cosine of the same inside function, x to the fourth, so I'm replacing that in there, times the derivative of the inside function, which is 4x to the third. And I almost made a mistake when I found that derivative, believe it or not. And so I put the 4 down in front and said to myself, there's a 5 down in front in my head, but I know that there wasn't. There's a 4 down in front. And the only thing that I would do about this is that I would rewrite it to make it look nicer, because usually you write monomials first. So I kind of am out of room, but I'll scoot it over and I'll squish it in here. 4x to the third times cosine x to the fourth, right? And then I gave you some songs, and I have played before during COVID time some of those songs in my video about the chain rule, because I know that these songs were made for people learning the chain rule, and then my video got taken down by YouTube for copyright, even though I only played 10 seconds of the song. So if you want to listen to songs about not forgetting the chain rule, then go and listen to some of these songs right here. Okay, so here they're asking us to find the derivative of the function, and so this one's perfectly the fundamental theorem of calculus. I have a constant down here, and then I have what I'm going to plug into my inside, which is my inside function, which is just x there. And since it's just x, I don't have to use the chain rule. And so this would be the derivative y prime equals cosine squared of x. Done. And so, but when I go here to do this one, notice it's the same function, exactly the same except for x to the fourth. This is my inside function. And so when I go find my derivative, what you do is you just replace your inside function, right? You make sure there's a constant down here, and you replace your inside function in there for theta. And so this would be cosine of x to the fourth. And then you have to do the derivative, right? Chain rule, right? This is the outside. This is finding the derivative of the outside, replacing the same inside, right? Just like we had up here. And then times the derivative of the inside. And since I have x to the fourth, the derivative of the inside. And so right here, I need times the derivative of the inside. Derivative of that inside function, which that inside function is x to the fourth. So that's 4x to the third. And so I missed the square right there. Sorry, I didn't mean to miss the square right there. I didn't miss the square over there. So you replace in, right? And then the only thing that I would do, just like I did on the other, is make it look a little bit nicer. Okay, so we did a lovely job on that, right? And so that was problem 18 on your book. And then now we're going to look at the fundamental theorem of calculus part 2. So that's what FTC stands for, fundamental theorem of calculus part 2. So what we were doing over here was the fundamental theorem of calculus part 1. So this was FTC part 1. And then this down here, fundamental, was down here. These right here were FTC part 1. That's what they were. And so, well, this one was part 1, and so was this one. This one's the only one that had chain rule in it. And so the other examples that I gave you did not have chain rule in them. Okay. So one of them had chain rule and the other 3 did not have chain rule. So this is the fundamental theorem of calculus part 2, and it deals with finding the net area is what it deals with. And so remember the notation that they gave you in 3.9. They said if you had a function f, and if you found the antiderivative, they called it capital F. And so what the fundamental theorem of calculus says, that if you want to find, remember this stood for the area that's trapped by the curve and the x-axis from A to B, that all you have to do is find the antiderivative and replace the upper bound minus the lower bound into that antiderivative. So F is the antiderivative of, capital F is the antiderivative of lowercase f. And that means that if I took the derivative of f, I would get, of capital F, I would get back lowercase f. Arnie wants you to know that you cannot find the antiderivative of every function. So Arnie was my office mate, and I was typing up these notes, and I was writing exactly what the book had about it. And he said, but Donna, you haven't mentioned that not every function has an antiderivative. And so, yes, so we'll be able to find the area that's trapped between the curve and the x-axis by using the antiderivative if the function has an antiderivative. And if it doesn't have an antiderivative, then we'll have to use something different. But we won't use something different in Calc 1 because they don't teach it to you until Calc 2. And so I understood what he was saying to me is that he was saying that me writing the theorem the way I did, which is exactly the way the book had it, was that I was indicating that that's how you could do it every time. When if the function didn't have an antiderivative, then you could not do that and would have to do something different. So this is called a definite integral, and it gives the net area between the curve and the x-axis from A to B. So that's what you're finding here. This is called the definite integral. So when it has bounds on it, it's called the definite integral. We've also are going to see later on integrals that have no bounds, and they're called indefinite integrals. And so whether it has bounds on it or not is what tells you that it's a definite integral. So this one right here is a definite integral. And so it asked me to find the answer using the fundamental theorem of calculus part 2. So what I have to do is I have to find the antiderivative. And so so I want to find the antiderivative of x. And I think that y'all probably remember that you put an exponent here, right? And you add 1. I mean, I know this all the way back 3.9. You add 1 to the exponent, which gives you 2, and then you divide by the same darn thing. So that the antiderivative of x is x to the second over 2. And you can check this by finding the derivative of this. If you find the derivative of this, you'll get x. So now what is the antiderivative of minus 6? So minus 6x. And in chapter 3.9, you always had the plus a constant. And I want to show you why you don't have to worry about the constant here. But I'm going to put the plus a constant so that I can show you why you don't have to really worry about it and you could ignore it. Is that okay? And so I'm going to put it, so the antiderivative in chapter 3.9, when they had us finding antiderivatives, we always had plus a constant. And I want to show you why on the definite integral, when you have bounds, that you don't need that constant. So I'm going to evaluate this from 1 to 10. And so I'm going to substitute in the upper bound minus the lower bound. That's what the fundamental theorem of calculus says. Find the antiderivative. They called it f. So here's my antiderivative. Right there it is. And then evaluate it at the upper bound minus the lower bound. And so I have my, and notice I am not writing the integral symbol anymore because I have found the antiderivative, and I am now just writing a straight up and down line to show myself to plug in. So I'm going to be plugging in right here. This is where I'm going to put in my upper bound. So this is my upper bound, which is x equals 10. And then right here, minus, this is fundamental theorem of calculus part 2, the lower bound, which was x equals 1. Okay. So right here, I'm going to be putting in 10 squared over 2 minus 6 times 10 plus c. And 1 squared over 2 minus 6 times 1 plus c. And I'm going to show you why you don't need the c. And some of you already see why you don't need the c. And so, and then when I just do the math here, That's 100 divided by 2, which is 50, minus 60 is 40. And so this right here is 40 plus C. And of course, I'm trying to convince you that you don't need the C and that you can just not have the C there. I want to make sure that that's right here, that that's 40. And the reason I'm going to check it more carefully than I just checked with my head is because I will tell you that if I had a dime for every single time that a person took the antiderivative correctly and found the antiderivative and then had problems with their arithmetic when they plugged those in and got the answer wrong because of that, I would be so rich that I would not be making these videos. And so, I mean, I would be sitting on a beach somewhere in a beautiful place. There's lots of beautiful places all over the world. Oh my gosh, I'm getting negative 10. And I said it was 40. Oh, I forgot to divide by 2. That's why you use your calculator, friends. And if I counted every time I made a mistake, so I put it in the calculator right there, right? 10 squared over 2 minus 6 times 10 is negative 10. If I had every time I made a mistake on it, since I do way more problems than most people, I would be so rich that I would own that beach. And so just from student mistakes, I would just be sitting on the beach, but from my own mistakes, I would be owning that beach. And so, but that's the reason. So I was not meaning to convince you that it's a good idea to do it both with your head and your calculator so that if you don't get the same value, you can say to yourself, holy cow. So now I need to replace 10 with 1. Oh, I guess I only needed to erase the 0. I can be such a dummy head sometimes. So I'm getting negative 11 over 2. And so remember, I'm going to convince you that you don't need the C, and so that you didn't really need to write that. So this is negative 10 plus C. And then when you distribute the negative, you could get plus 11 over 2. And then minus C. And see where the C's are going to cancel out. Would the C's cancel out every single time? And the answer is yes. If you put the plus C, then you're going to have plus C here, minus C here, in your upper and your lower bound. So do I have to have the C there? And the answer is no. So do people put in the C when they're doing a definite integral? And the answer is no. It's confusing. So you wouldn't want to do that. Why did I put it in this one particular example? To show you that you didn't need it, because otherwise people are going to ask me, I thought when you told me in 3.9, when I took an antiderivative, I needed plus C. And you're right. In 3.9, when you took an antiderivative, you needed plus C because you were not doing a definite integral. You were doing something different. So now I'm going to put this in my calculator, and I'm going to get negative 10 plus 11 over 2, which is negative 9 over 2. Not 9.5. What am I doing? Negative 9 over 2, which is negative 4.5. So that is this integral, right? Which was from 1 to 10 of x minus 6 dx. Okay. Now that integral, remember, was supposed to find the net area. So I want to show you, this is not a proof of the fundamental theorem of calculus part 2, but it's showing you that, hey, it worked to give the net area. And so that's all that I'm wanting to do here is I just want to show you that it does give you the net area. If you want the proof of the fundamental theorem of calculus part 2, go to your book. It has a proof. And if not, go to YouTube and type in YouTube proof of the fundamental theorem of calculus part 2, and you'll get to choose from 1,000 different ones if you like. And so and come to my office and me and you can watch a video together and figure it out. So right here I've given you a graph of y equals x minus 6. And if I want to find the integral from 0 to 10, not 0 to 10, 1 to 10, I wish I would have done 0 to 10, that would have been better, but 1 to 10. So I have to go here from 1 to 10. Then what right here? Oh, this problem came out of your book probably, and that's probably why. Okay, then I'm going to find this area right here trapped between the x-axis and the curve, which the curve is a line. And this area over here, this is crossing right here at 6. And this area from 6 to 10, that's above the axis. And it is 2 triangles. So this triangle right here, the area of this triangle is 1/2 the base times height, right? And 1/2, and the base is, it's going from 1 to 6. So the base is 1 to 6 is 5. And then it has a height. This is its height right here. And that height is 5. So, and remember, because it's on that side, right? It's going to be counted as negative. So this is 25 over 2. That's the area, but because it's below the x-axis, the integral is going to count it as negative. Let's find this other one, and then we'll put it together. Okay, so this other area, 1/2 is a triangle, base times height. So that is 1/2, and the base here goes from 6 to 10, so that's 4. And then the height, 1, 2, 3, 4. So the area here is 8. And I didn't use my calculator, so I hope I'm right on that. And then if you're wanting to find this integral, the integral from 1 to 10 of our function x minus 6 dx using geometry, then we had this area that was below the x-axis, so that's negative 25 over 2. You count it as negative because it's below the x-axis, plus 8. And we know that that answer better be 4.5. If it's not equal to 4.5, then we know that we have a mistake somewhere on one of them, because we did it both ways. And so we did it geometry, and we did it using the fundamental theorem of calculus part 2. So I'm putting this in my calculator, negative 25 over 2 plus 8. And I'm hoping that is, negative 9 over 2, which was 4.5, negative 4.5. Either way, I never round, right? So if it came out to be something that, as far as I can write things as a decimal, but I shouldn't round. And so if it had, instead of being negative 9 over 2, had it been 7 over 3 right there. And when I hit S to D, I get 2.3333333333, and I have to round in order to write it as a decimal. So I would want to write that one as a fraction. Negative 4.5 or negative 9 over 2 are equivalent to one another. So it doesn't matter which one I put. They're exactly equal to one another. Okay, whereas 1/3 is not equal to 0.3. And that's the reason it's not even equal to 0.333. You have to round in order to write it out. And people don't like the notation. It is preferred to use 1/3 versus using 0.3 with a line over the top of it. I guess those are exactly equal to one another. But this 1/3 is definitely preferred. And so this is just a little discussion on exact versus rounding. And it's always preferred in math to do exact, right? Engineers might round, but math people do exact because that's how we are. Okay. So evaluate the following integrals using the fundamental theorem of calculus part 2. And then I just gave you the graph of it. And the only reason I gave the graph of it is not to prove the fundamental theorem of calculus part 2, but just to keep re-emphasizing what the heck you're finding, right? So that's the reason for that. So we're in learning mode, and so that's the reason that I'm doing that. So if I want to find the antiderivative here, I have a product, and you cannot find the antiderivative of a product straight out. So you can't find the antiderivative of one piece and then multiply that by the antiderivative of the other piece. And it would be really great if you could, but you can't. So what you have to do is you have to multiply first. So this would be the integral from 0 to 4. And when I multiply this together, now if it makes you happier to have your square root of t written first, then this would look like this. And if it makes you happier to write t to the 1/2 when you go to multiply this together instead of the square root of t, then go ahead and do so. And so you do you on that. And now I'm going to multiply these together. So this is going to be 4t to the 1/2. And remember what you do, you add the exponents, and 1 plus 1/2 is 1.5. So this is minus t to the 1.5 dt. And then technically I would need parentheses around this, but I don't get too crazy about it, I have to admit, because I say that I'm trying to take the antiderivative between those two symbols. dt is a symbol and the integral symbol is a symbol. This tells me to take the antiderivative with respect to t. And that really becomes important in Calc 3, because in Calc 3 you take we don't do it in Calc 2 or Calc 1, you take the antiderivative with respect to a variable that's not there. Now you might be saying, oh, we didn't do that with our derivatives, but yeah, we did. It was called implicit differentiation, and we did, and they're going to do that later, but they don't do it here, thank goodness. Okay, so the 4 holds still. So that 4 holds still. You cannot put the 4 in the front because there's not 4 as part of this. And so the 4 can't be moved to the front, but you can just say that it holds still. And then I take the antiderivative of 1/2. And how you take t to the 1/2. So how you take the antiderivative of t to the 1/2, this is what's going to happen on the exponent. You're going to take 1/2 and you're going to add 1. And when you do that, you get 1.5 or 3/2. I'm going to write it as 3/2. You'll see why. And you can use your calculator to do that. So this is going to become, and I'm leaving a little bit of space, at t to the 3/2. And then what you would do is you would divide by 3/2 is what you would do, right? Because you divide by the same darn thing. But when it's a fraction, I'm a lazy person, and so I say to myself, if you're going to be dividing by 3/2, that is the same as multiplying. So that is the same as multiplying by 2/3, the reciprocal. So I don't do this. I don't divide by 3/2. You can. I'm fine with that. What I do is I say this is going to be 4 times 2/3 multiplied by the reciprocal, and then t to the 3/2. But you do you. And I've written so big that I'm going to run out of room on something that I should not be running out of room on. And so I'm embarrassed, I'm humiliated, whatever have you. I wish I wouldn't have written that as 1.5, but at the time that I wrote it as 1.5, I don't know, I was chewing gum, but I wish I would have wrote it as 3/2. And so now I'm going to do that next exponent. And when I do that next exponent, it's going to look like 3/2 plus 1. And I'm going to do that on my calculator. And when I do that on my calculator, I get 5/2. And so this is going to become, I'm going to write it down here. And in fact, I'm going to erase that. Is that okay if I erase that? Because I'm going to run out of room. Does anybody care? Would anyone hate me? For how long? 5 minutes hating me, or just 10 minutes? Or I don't think you can hate me over it, can you? And you're like, but I was writing in pen. And then I'm like, don't do math in pen, please. I don't do math in pen. And so I don't think anyone in our class does math in pen. So this is going to be minus, and this is t to the 5/2. And because that's a fraction, instead of dividing by 5/2, I say, well, dividing by 5/2, because you divide by the same darn thing, is the same as timesing by 2/5, the reciprocal. So I come right here and I times by 2/5. And then we learned in the last problem that, so there's my antiderivative. Yeah, that's 8/3 right there. And we learned in the last problem that you don't have to put the plus c. And so we're going to go from 0 to 4. And so this is going to look like the upper bound. So this is 8/3 and t to the 3/2 minus 2/5 t to the 4 raised to the 5/2. That's the upper bound, minus the lower bound. And this is where I'm a little bit of a lazy person, but I have to be careful sometimes with my laziness. When I put in 0, that wipes that out. And when I put in 0, that wipes this out. So this is 0. And then I can just put that part in my calculator. If I had a dime for every time that a person messed this part up, this part where you do the substituting in, found their antiderivative correctly, and then messed up that part of it, I'd be so rich. I already said that I would buy, that I would be sitting on an island. And if I used all the times that I made mistakes, I would be buying that island. And so that is why I do like to use the calculator. And I'm really grateful to have a calculator that you can just put it in just like you see it. When I was a student, you had to do it by hand, and that was where I made a lot of those mistakes, is doing it by hand and not thinking correctly. I decided to put in 5 divided by 2 instead of 5 halves with a fraction key, but you can put it with your fraction key. So I'm getting 128 over 15, which is the exact answer, and that's what us math people want, right? So 128 over 15 is my answer. And I just want to do the approximate so I can convince you that that's what this area is over here. And so that's approximately, now they're not asking for the approximate answer in your book, just so you know. And so, which is approximately, so I just put S to D 8.53 with a line on it. 8.53. And so really 8.5, right? So I want to come over here and I want to see if we can be convinced that the area here is around 8.5. So I have the area that we're talking about is under the curve and trapped by the x-axis from 0 to 4, right? And so I have some whole boxes. So right here is a whole box. 1, 2, right? Here's another whole box, 3. And then I have, this is almost a whole box. And so these 2 boxes, these 3 boxes up here, to me, look like when you put them all together, and I've counted them like that, and that was a really dumb way of counting them. But this is 1 box, 1 box, 1 box. So there's 3, right? And now I'm circling this right here, and I'm going to say that that to me looks like 2 whole boxes up there, because this is a part box, that's a part box, and a part box. And when I put them all together, maybe 1.5 boxes actually, now that I'm thinking about it. Sorry, 1.5 boxes now that I'm really getting into it. So I think that's 1.5 boxes, those 3 boxes. Then I have this box and this box together right here that that looks to me like 1.75 boxes is what it looks like. And then I have almost a whole box right here, but I'm going to call it 0.9 of a box, 0.8 of a box. Maybe I should call it something 0.75 of a box. And then I have a little chirp of a box right there. And so I'm going to put those together and say that's actually a whole box. So this little spot right here, I'm going to say that's 1 whole box. And then this is a partial box right there. And I don't know, it's nipping off a whole bunch of it. It's more than half, maybe 0.6 of that box. And then when I add those all together, it should be really close to 8.5. And of course, I didn't do it exact, friends. I just tried to 4 boxes there and then 0.6 of a box. I'm just trying to convince you that it's around, so 7.85. So I've underestimated in some places. I was hoping to at least get to 8. And so you can go and you can see where you think I might have overestimated. I only called this 0.6 of a box, and it's definitely more than 0.6 of a box. And this was more than 1 for certain. Those were whole boxes. I called this 1.75. I think it was probably more than that too. And this is, anyway, just so that you can see, that's what you're finding is that area under that curve. And so I just tried to estimate the area. And of course, a little off here and a little off there makes a lot. Here, this is one last idea that they have in this section. So they're asking me to find this definite integral, which is and they don't stress on this. They mention it here and then don't stress on it in Calc 1, but they do stress on it in Calc 2. So if you're like worried that, oh my gosh, I might forget to check this or I might miss it, for Calc 1, you'd be pretty safe. And then in Calc 2, you're going to have to be more careful. But you'll have more things under your belt, so you'll be fine by the time that you get there. And so if I just, this is a definite integral, and it's supposed to represent the area from -1 to 2, right? And if I don't, notice that, hey, between -1 and 2 is 0, and 0 makes this undefined, makes my function undefined, and I just go blindly about it. Okay, so they found the antiderivative. They did not show you any work in finding the antiderivative. They just did it, right? And then I use the same thing that they use in the book, which they kind of use a little like that. I use a straight up and down line because that's what I was taught in the calculus book I learned out of, which is Thomas. And so, but I'm good with either. But you don't use the integral sign because you found the antiderivative. And so, and then and evaluate from -1 to 2. So upper bound minus lower bound, you get 3/2. And so then you're saying that that's what that area is. And they're asking us here what went wrong. And so I've drawn the picture over here so that you can see. Here's -1. And this area right here is going to, because there's an asymptote right here. So that's going to, that area is like going to infinity, and then going over here to 2 and negative, right? Because it's below the x-axis. And this area over here is above the x-axis. So you really can't put these together and say that area that you have there, this area being size -infinity, and this area being size infinity, and say you get 3/2. And so there is going to be some things that you're going to look at with this in Calc 2. And so we're not going to, but the problem is, so what went wrong is that you can't do the fundamental theorem of calculus and say that's going to give you the area if it's not defined from -1 to 2. So if there's any place, I guess the directions on it were, is it had to be, I'm just coming back over here, is that this had to be a continuous function on those bounds, negative from A to B, right? And so what went wrong here, why this is not going to work, is that f at x right here being 4/x⁻³ is not continuous on the interval -1 to 2. It's discontinuous at x = 0. There's an asymptote at x = 0. So a discontinuity happens at a hole in the graph, at a asymptote. We have an asymptote, right? And so, but I did tell you that you weren't going to have to focus on this, that they were going to ask you every now and then, but they try to make it clear that something is going wrong. And so, and then in Calc 2, they will just ask you this integral, and if you just blindly do it, you'll have the wrong answer. And then I have a warning from James Stewart, and the warning is you should distinguish carefully between the definite and the indefinite integral. So this is called a definite integral, and the definite integral has bounds, and when you find it, you get a number as a result. Whereas the indefinite integral, and that's what we're going to be learning about in the next section, is a function or a family of functions. And we found those functions or the family of functions in 3.9. And so that's all that he wanted to say. The next part of his story we're not really worried about. And that's my story on 4.3. Very happy to be done with it. And because I've made 3 videos back to back, I hope you didn't watch 3 videos back to back. I hope that you take a break in between them. And I hope that, that you're having a good day.